Yes, ma'am.
Okay. See, the problem that we started with, that's the first problem actually, which was x square minus 1 y double dash plus 4xy dash plus 2y equal to 0. Okay. Now, in this case, your ax was x square minus 1, your bx was 4x, and your cx was 2. If you compare it with the general differential equation of second order, right? Now, we have seen, like when we discussed, of course, using this a and b, we can define our px, which is nothing but bx upon ax, and your qx was nothing but cx upon ax. Okay. And for a differential equation, to have a power series solution, we wanted both p and q to be analytic, right? Now, where will they be analytic? Where the denominator does not vanish. That means all those x for which ax is non-zero, right? Now, such points for which ax is non-zero, we had called as ordinary points, right? Now, the point is that when I am given a differential equation, it's easier for me to find the points for which ax is 0 rather than talking of those points for which ax is not 0. Okay, that is why we say that any point which is not an ordinary point is a singular point. Is this clear? Okay, it's like in this case, my ax is 0 for when my x square minus 1 is 0, that means x is equal to plus minus 1. That means for my given differential equation, x equal to plus minus 1 are my singular points. Okay. Now, when we are finding a power series and we are writing the series in the form Cn x to the power n from 0 to infinity, that means in this case, my a happens to be 0. Now, when I say plus minus 1 singular points, that means I cannot have series in the form x minus 1 to the power n or x plus 1 to the power n. Why? Because they are not, or plus 1 and minus 1 are not the ordinary points. So we cannot talk of power series around that. But we can definitely talk of power series for this particular differential equation, because 0 happens to be an ordinary point here. Okay, so that's why we need not specify what exactly we are doing. We just specify that, okay, these are the two singular points. Fine, I'll go ahead because I have to start my series solution with something like this. Is this clear now?
Yes, ma'am.
Okay, so now that's why we start with, okay, let my y be this summation Cn xn, as we've been doing earlier. The rest of the procedure remains the same. It does not change. Okay, but because plus 1 and minus 1 were my singular points, and as per the theorem that we discussed, so we know that radius of convergence is at least 1. It will always be more than or equal to 1 because it has to be the distance, of the ordinary point from the nearest singular point. And what is the ordinary point in this series? 0. What is the nearest singular point? Either minus 1 or plus 1. It's like this. This is your ordinary point. You have two singular points here. So we are not considering these points. But the distance, why 0 is an ordinary point? Because I am talking of a series solution of this form, which is actually nothing but Cn into x minus 0 to the power n. So basically, your radius of convergence is at least going to be as large as the distance of the ordinary point from the nearest singular point. And your singular point, that's why the theorem says it can be real or complex, because you might come across differential equations where your ax is something like this, x square plus 4. So when does it become 0? That means when it's x is plus minus 2 iota. So in this case, your singular points are not real, but they are complex. So we can talk of the distance of the ordinary point from the nearest singular point. That will also define the minimum radius of convergence in that case. So it's similar. This particular thing has been discussed, I think, in example number 4, if I'm not wrong. Let me cross check once again. Yeah, that's example number 4, where you have complex singular points. Then also we can talk of the radius of convergence, which would be at least as large as the distance. Okay, so once you have identified your singular point, so you can immediately, like in this case, it were real numbers. So we can immediately say that the radius of convergence would be at least this. That's it. Then you start with finding the series solution because we are finding it around 0. So we are confident that a solution will exist. And it would be a convergent solution, definitely. Okay, but see, sometimes what happens is, like, for example, I think it's your, this was the first problem, 8.2. Yeah, the third problem, if you just look at that, it's y double dash. Question number 3 is something like y double dash plus xy dash plus y equal to 0. Okay, now in this case, your ax is 1. So it never vanishes. That means this particular differential equation has no singular point. Okay, so because it has no singular point, so that means your radius of convergence will be what? At least infinity. And when rho is infinity, what happens? The series converges for every x. Okay, so that means in this case, you can find a power series of this form, and this series will be convergent for every value of x. There is no limitation on that. Is this clear now? Huh?
Yes, ma'am.
So do you want me to do, I mean, I don't need to solve the problems again because you've learned how to solve them. बार बार series करने का तो कोई फायदा नहीं ना, मैं बार बार करूं, या or you want me to do it? I don't know. I mean, you know now how to change the indices, you know how to adjust the summations by changing your ends and so on and so forth.
Yes, ma'am.
कर लोगे ना आप अपने आप?
Yes, ma'am.
Yes, ma'am.
Okay, so it's like the first 15 problems are of a 8.2 are based on this only. Okay, where you have to solve it like this, right? Then again, like we have talked of initial value problems, so in a similar manner we can talk of the initial value problems here also. So your problem number 16 and 17, they are both your initial value problems. So you have, you know, a differential equation like this, plus 2xy dash minus 2y equal to 0. And you are given that y at 0 is 0 and y dash at 0 is 1. So the procedure now remains the same. That now see, you have a second order differential equation where your coefficients are functions of x. So that means we have to verify that we are finding a series solution around an ordinary point. So we just rule out we find the singular points and we observe that x equal to 0 is not a singular point. And therefore we can find a series solution for that. And then once you have your yx, you use your initial conditions, you get the values of C0 and C1, and then it's done. Is this okay? Right. But sometimes what happens is, like for example, your question number 18, just look at this. It's y double dash plus x minus 1 y dash plus y equal to 0. Okay. The initial conditions that you are given is that y at 1 is 2 and y dash at 1 is 0. Now this is a little tricky. Okay, so we have to pay attention here. See, in this case, yes, of course, my differential equation is okay, fine. And since my ax is a constant coefficient, so obviously that means no singular point. Therefore, it is convergent for, the series solution is going to be convergent for every x. So that part is fine, right? Now, the point is that if I am given initial conditions about the point, about some point, see, when we say series of this form or series of this form. There is a difference, right? Here you are talking of the power series around 0. Here you are talking of the power series expansion around some point A, right? Now, the thing is that if I am talking of this kind of a thing, right, then my initial conditions should be around the point 0 only. Okay, but if my initial conditions are given around the, see, that's why all the earlier problems that we have done, even the problem number 16 and 17 of this equation that I was talking of, there the initial conditions are given when x is 0. So that is why we go ahead with this series, we use the initial conditions and we get the values. But in this case, what is happening is that my initial conditions are about 1. Right? So in order to use these initial conditions, I should have a series solution in this form. Then only I'll be able to. Why? Because it has been proved. We can say that to solve an initial value problem, we need a series expansion of the general solution concerned at the point where the initial conditions are specified. Okay, so just keep this in mind. So that means the moment we are given a differential equation, we not only have to see the coefficients and identify the singular and the ordinary points, but we also have to look at how the initial conditions are given. Okay, if they are given about some point A different from 0, then this is the series that we should be talking of, right? But the problem is that it becomes cumbersome if we start with this as the general solution. Okay, so that is why, and since, see, in mathematics, we have an operation called as translation, where we can always shift it's like shifting your origin, like instead of 0, now your origin will be A. So it's like so this was 0, this is A. So we are we are picking up our number system, real line, and shifting our origin from 0 to A. And this process is called as what? Translation. Okay. So that means we have another method of solving where we can translate the solutions. So in this case, what we do is we simply, like this was n, so we simply make a translation where we say that that means instead of x now, we define our new independent. See, now we have to keep in mind this also. When we are talking of a differential equation or the derivatives here, we are talking of dy by dx. So that means we are assuming that x is the independent variable and y is the dependent variable. Okay, so when we are going to do the translations have to be done for x, which happens to be your independent variable. So that means we are now redefining our independent variable as x minus 1, whatever is your 1. So basically you are defining was t equal to x minus a, right? So the moment we translate, that means we are changing our x to t now. Now, since we are changing our independent variable here, that means the derivatives also need to change a little bit. Okay, let's see what happens. When your t is x minus 1, that means your x is t plus 1. Okay, that means, from here, I can conclude that my dt by dx will be 1 from this equation only. Okay, now see, now, in order to rewrite my differential equation, I must have dy by dt instead of dy by dx. Okay, but my dy by dt is nothing but dy by dx into dx by dt. Okay, so whether I use this to write dt by dx is 1 or I use this to write dx by dt is 1, they mean the same thing, right? Now, what is dy by dx? Y dash. And what is dx by dt? 1. Okay, so that means with this as my new change of variables, my dy by dt still remains y dash. There is no change in that. Similarly, what will be d2y by dt square? This will be d by dt of dy by dt, right? Which will be nothing but d by dx of dy by dt into dx by dt, right? So that means what? D by dx of y dash into 1, which is nothing but y double dash. So in this case, they're not changing. Okay, so your d2y by dt square is still your y double dash. Okay, so that means your differential, the new differential equation now becomes, see what was the first term, y double dash. So it still remains y double dash. What was the second term? X minus 1 y dash. But what is x minus 1 now? T y dash. Okay, plus y equal to 0, where we now mean that y dash is now dy by dt and y double dash is now d2y by dt square. Okay. Now see, what about the initial conditions? We were given the initial conditions y when x is 1, and this was given to be 2. Yahi tha na? Can you just cross check? What was it? The initial condition. Did I mention? Yeah. Y at 1 was 2 and y dash at 1 was 0. Okay. So y when x is 1 was 2. But how much is your t? X minus 1. So when x is 1, what happens to t? 0. So that means y when t is 0 is 2. Similarly, y dash when x is 1 was 0 implies y dash when t is 0 is 0. That means my differential equation is actually now solving this, where we are given that y at 0 is 2 and y dash at 0 is 0. Is this clear?
Yes, ma'am.
Yeah. So in a way, we have translated our given differential equation, but now my initial conditions are back in terms when what is 0? T, not x. So my new variable now is t. So that means in this case, I have two variables, y and t, where y is the dependent variable and t is the independent variable. Whereas my original differential equation is in terms of y and x. Okay, so now that means the power series solution that we are going to start with will be something like Cn t to the power n and not x. Okay, because we are now writing the series, we are finding the series solution in terms of the translated variable t. Okay, so with this as y, now the remaining procedure remains the same. Your y dash is n Cn t n minus 1, n from 1 to infinity. Y double dash is n minus 1 Cn t n minus 2, n from 2 to infinity. Now you can substitute in the differential equation. Now can you solve it simultaneously? What do you get? What was the first term? Y double dash. So n from 2 to infinity, n minus 1, c n t n minus 2 plus t summation n c n t n minus 1, n from 1 to infinity plus summation c n t n from 0 to infinity equal to 0. Okay. Now again, maybe I'll just tell you quickly how to do this. That means your equation is now summation n minus 1 cn tn minus 2 n from 2 to infinity plus. Now the second term becomes n cn tn, but your n varies from 1 to infinity, right? Plus summation cn tn n from 0 to infinity equal to 0. Okay, now like I said, it's a very crude rule, but then we want every term with t to the power n, right? And we want the summations to be starting from 0. Okay, now this term is fine, no issues with that. But if I just look at this term, I have to t to the power n, but then my summation is starting from n equal to 1. So in such cases, it's the best way is to check. If you start the summation from n equal to 0, will the series change? Okay. If no, then we can directly write the summation from n equal to 0. Now, in this case, will not change. Why? Because you already have an n here. Okay. So when you are starting summation from n equal to 1, you are actually, now this is the rough work I'm doing. When just look at the series, this is actually starting with C1t plus 2C2t square and so on and so forth. This series you get when you start n equal to 1. But what happens when you start from n equal to 0? The first term is 0 plus C1t and so on and so forth. So it does not make any difference. So that means without changing the index, we can directly convert our summation from n equal to 0 to infinity. But in this case, it won't happen. Why? Because we have an n minus 2 here. Okay. So to change this n minus 2, we need to change our n to n plus 2. And accordingly, our starting point reduces by 2 units. So we get n from 0 to infinity, n plus 2, n plus 1, c n plus 2 tn plus. This I write from 0 to infinity n c n tn plus summation n 0 to infinity c n tn equal to 0. Is this clear? So basically, what you get now is summation n from 0 to infinity. Now your tn is common. Okay. So what will be the terms? Can you just quickly write? क्या क्या आएंगी? n plus 2, n plus 1, cn plus 2 and cn का कोफिशिएंट अब क्या बन जाएगा? Plus, how many terms with cn? 2 terms, na? N plus 1, yeah. You're going to get n plus 1 cn equal to 0. So I'm now directly writing my cn plus 2 is nothing but minus n plus 1 cn upon n plus 1 into n plus 2. Which means your cn plus 2 is nothing but minus cn upon n plus 2. ठीक है ना? So this becomes your recurrence relation. So for n equal to 0, what do you get? C2, which is minus C0 by 2. For n equal to 1, you get C3 minus C1 by 3, and so on and so forth. So can you just give me the series that you get? Just give me a direct expansion. I am okay with that. Anybody can give me. Now see, your y is now, what you are getting is yt. So I'm getting C0 plus C1t to aega hi aega. What will be the next term? Minus C0 by 2t square. Then what is the next term? क्या है अगला टर्म? What is the next term? Next. कोई तो बोलो. What is the next term?
Plus C naught upon 2 into 4 t to the power 4.
Okay. Plus C naught upon 2 into 4 t to the power 4. Okay. So this will be plus t to the power 4. And what about the next term? Along with it, at least find till 6, 7 terms minimum if you're not generalizing.
Ma'am, plus C1 upon 3 into 5,
Yeah,
10 to, t to the power 5.
5, right. So this will become plus t to the power 5 upon 3 into 5. Okay. And I think because you've got alternate plus minus, so better verify from the next term also. So at least one more term. That's what I'm saying. At least find 8, 7, 8 terms if you are generalizing. I mean, if you're writing the expansion, it's always better. Because I think you won't be getting a general term here. Fine, it does not make any difference. And so on and so forth. It will be something infinite, but just give me 2 more terms here. I think all odd terms are coming here, so it should be t to the power 6.
2
And
into
it should be
4
alternate plus minus, so it should be minus t to the power 7 upon something, and so on and so forth. Just give me the denominators now.
Ma'am, 2 into 4 into 6.
2 into 4 into 6. And it should be 3 into 5 into 7.
7.
Okay, na? Now, with this as y, we can find our y dash, which will be nothing but c naught into, now just differentiate this series. It will be minus 2t by 2 plus 4t cubed by 2 into 4 minus 6t5 upon 2 into 4 into 6, and so on and so forth, plus c1 into 1 minus 3t squared by 3 plus 5t4 by 3 into 5 minus 76 by 3 into 5 into 7, and so on and so forth. Now use the initial conditions that y when t is 0 is 2 and y dash when t is 0 is 0. Now use the initial conditions to get the values of C0 and C1. So how much is your C0 and how much is your C1? Just compute that.
Ma'am, please show the previous slide.
Yeah, just is this okay?
Yes, ma'am.
Ma'am, C1 is 0 and C naught is 2.
C1 is 0 and
C naught
C0 is
is
2. Right. Okay. So you're getting your C1 to be 0 and C naught is 2. That means your typical particular solution is actually, so we'll substitute the values in this solution that we obtained, right? So it, sorry, not this was y dash, this was your y, right? So we'll substitute here. So since C1 is 0, so that means this term vanishes. Okay, so that means we are left with only this term as the solution. So your solution now becomes yt equal to 2 into, what was that? 1 minus t square upon 2 plus t to the power 4 upon 2 into 4 minus t to the power 4 upon 2 into 4 into 6 and so on and so forth. Okay, but mind you, this is a power series in terms of t. Okay, but our actual equation, the problem is in terms of x, right? So since we substituted, so what is your t actually? X minus 1. So basically your solution yx is nothing but 2 into 1 minus x minus 1 square by 2 plus x minus 1 to the power 4 by 2 into 4 minus x to the power 1 by 6 into 2 into 4 into 6 and so on and so forth. So this becomes your solution, the initial value problem solution. Okay, so remember, we did not start with the series of this form. Okay, we simply changed our variable. Instead of x minus a, we started with the t. Because it's easier to find the solutions in this manner, around 0. So we found a solution around t, and then in the final answer, we substituted back our original value. Is this clear? But sometimes, like for example, your question number 20th, right? See, it says x square minus 6x plus 10 y double dash minus 4 into x minus 3 y dash plus 6y equal to 0. Okay, and the initial conditions that we are given is y at 3 is 2 and y dash at 3 is 0. Okay, so as I was saying, it is the initial conditions which will define what translation you have to make. Okay, so it's like basically your a is 3 in this case, right? So we'll define our t as x minus 3, the way we define t as x minus 1 in the earlier problem. Okay, now in this case, if I define this as my t, obviously this remains, this gets converted to t. But if I just look at this, I have to do a little modification in the sense that, I mean, any guesses? We can always, it says x square minus 6x. So definitely it has got to do something with x minus 3 whole square. Okay, so but then I have a plus 10 here. So this is actually nothing but this y double dash. Is that okay now? Minus 4x minus 3y dash plus 6y equal to 0. Now, of course, when you substitute, you verify that your y dash, y double dash do not change. So this becomes simply t square plus 1 y double dash minus 4t y dash plus 6y equal to 0. Now you can see your singular points are plus minus iota. So 0 is not a singular point. So that means you can find a series solution of this form, Cn t to the power n, where n starts from 0 to infinity. Is this clear?
Yes, ma'am.
Hmm? So basically, because this immediately we can conclude, I mean, of course, given this, we'll say that t equal to plus minus iota are the singular points, which implies that t equal to 0 is an ordinary point. We have to specify, we have to be sure that whatever series solution we are writing, we are finding it is about an ordinary point. Okay? Is this clear? Now you can proceed on the way we did in the earlier problem. You find your CNs, you use your initial conditions, and then you get the solution. Is this okay?
Yes, ma'am.
Yes, ma'am.